Jai Hind to all. My name is Dr. Divya Sharma, Assistant Professor in Ajay Kumar Garg Engineering College, Ghaziabad. Now, today's video lecture is on VLSI. Its code is BEC701. Now, in this lecture also, we will discuss testing. So, we will continue this testing process here. So, next, we will discuss here this technique BIST. It stands for built-in self-test. So, this built-in self-test design, here parts of the circuit are used to test the circuit itself. So, these are the two types of BIST are there. Online BIST that perform testing during the normal operation. Now, second type is offline BIST that perform testing when the circuit is not in a normal operation. Now, there are some essential modules required for BIST. What are they? That is Pseudo-Random Pattern Generator that generates test input patterns. Now, the second is Output Response Analyzer that stands for ORA that analyzes and compare the output responses of the circuit. Now, both this Pseudo-Random Pattern Generator and Output Response Analyzer that is implemented using Linear Feedback Shift Register that means LFSR. So, first we will study the Pseudo-Random Pattern Generator. To test a circuit, we have appropriate test pattern first we have to generate this. Now, test patterns can be produced using Pseudo-Random Pattern Generator, Weighted Test Generator, Adaptive Test Generator and other test generation methods. Now, Pseudo-Random Generator can be implemented using a Linear Feedback Shift Register. Now, here you can see this. This is a whole circuit. First, we have to start with this PRPG. It means Pseudo-Random Test Generator. Now, here next step is circuit under test. So, we have to apply here inputs to this circuit under test and we are getting output from here this circuit under test. Now, ORA. So, here this is a response analyzer. So, we have when we are applying input and we are getting the output. So, we have to compare the output which is generated from the circuit under test and what should be the output, actual output for that logic. So, we have to compare here. We have to analyze here. If there is an error, it means the circuit is fail. If there is no error, then circuit is pass. So, this is the step where we have to analyze the output of this whole circuit. Now, so this diagram, so already we have discussed that first we have to start with this Pseudo-Random Pattern Generator, then your circuit should be under test. We have to apply inputs for that circuit and we will get the output for that circuit. So, we have to compare the computed output with the actual output and if there is an error, then circuit is fail. If there is no error, means your expected output is approximately equal to the actual output, then your circuit is pass. So, what are the steps we have to follow? So, here first is signal. We have to do a signal description that we have to start with the triggering the Pseudo-Random Pattern Generator to begin the test pattern generation. We have to give a pin in and pin out that represent normal external input and output of the circuit. We have to test here the circuit is pass or fail. The final result from the response analyzer indicated that the circuit is pass or fail, means circuit is properly tested, means your expected output is correct or not. Now, in this whole description, so here first is Pseudo-Random Generator. So, its function is to generate test patterns automatically and input a start signal initiated the pattern generation and output that input is going to the circuit under test that sends the generated test vector to the circuit under test at the output stage. Now, we have to do an implementation. That implementation is done by Linear Feedback Shift Register only. Now, second step is circuit under test. The function of the circuit under test, the main circuit or logic block being tested by this circuit under test. What are the inputs for this? Pin in, normal input pins of the circuit and test patterns from the Pseudo-Random Generator. Now, output for this circuit under test, pin out is the output responses produced by the circuit and these outputs goes to the response analyzer for analyzing the output. Now, that is the third step, output response analyzer. Its function is analyze the output from the circuit under test to determine if the circuit is functioning correct or not. Now operation for this ORA means output response analyzer, that compares the output response which is getting the from the circuit under test. We have to compare this one with the actual circuit, and we have that produces the circuit result, that fail or pass. So these are the steps we have to follow when we are doing this BIST technique, when we are implemented this. So now we are going to this linear feedback. What do you mean by linear feedback shift register, which is used in this BIST technique? So this circuit represents a pseudo-random sequence generator using a linear feedback shift register, that is a common component in built self-test system for generating test pattern. Now what is this here? First we will start with the circuit description. So this is a circuit. Here you can say this is XOR gate. 3 D flip-flops are there. Here is a clock which is connected to all these flip-flops, and we are getting this is a D flip-flop, first flip-flop, we are getting output in the form of Q0, and second D flip-flop we are getting output in the form of Q1, and the third D flip-flop we are getting output in the form of Q2. So this is a pseudo-random sequence generator using linear feedback shift register. Now here, this is the description, that 3 D flip-flops are connected in series here. Each flip-flop produces output in form of Q0, Q1 and Q2, and output of this Q2 is connected to this XOR gate, this XOR gate's output is connected to the first D flip-flop. So this cycle will repeat when we are getting the output from this D flip-flop, that is the input of this XOR gate, and one input is also connected to the first D flip-flop, then only you are getting this output of this XOR gate, and that is connected to the input of this D flip-flop. So here, now if we are doing this circuit, we have to implement this circuit, then on every clock pulse, the content of the flip-flop shift one position to the right. So input of first flip-flop, this one, is generated by XORing some of the flip-flop outputs that is known as tap connections. Now XOR feedback introduces a deterministic yet seemingly randomly sequenced zeros or ones, hence the name its name is pseudo-random sequence. So after a certain number of clock pulses, the same sequence repeats periodically. Let us take an example of 0, 0, 1. So here D flip-flop means we are giving here input 0 and we are getting output here 0. So here 0 is the for Q0, and if we are applying here this one is 0 for this D flip-flop, we are getting here 0, and if we are applying here 1, then you are getting here 1 for this. Now for this output for this XOR, it means here we are applying 1 and here we are applying 0. So we have to apply here the truth table of XOR gate. So we are getting the output for this first D flip-flop. So this is, we have to find out, and this one is shifted to here 0 and this one is shifted to 0. So like this we have to do all these steps, and when we are getting the same output, which is firstly we are applying here, then it repeats. So what are the here when it repeats, so what is the sequence length up to 2 to the power 3 minus 1? It means 7 unique states excluding all the zeros. So this is the sequence length for this circuit. Now if initially we are taking a step of 0, 0, 1, the sequence generated might be look like, if we are taking an input 0, 0, 1, then next state is 1, 0, 0, next state is 1, 1, 0. So up to this, so here this is the last one 0, 1, 0, because after that it will repeat that 0, 0, 1. So this produces 7 unique patterns before repeating this. So this is all about 3-bit linear feedback shift register. So what are the key points for this linear feedback shift register? XOR gate defines the feedback connection, or you can say tap sequence. Now pseudo-random because it appears random because but it is actually deterministic and repeatable. Now it is used in BIST to generate test patterns as a pseudo-random pattern generator. Now it is efficient because it requires only flip-flop and XOR gate yet to generate a long sequence. Now, what are the applications of this linear feedback shift register? First one is pseudo-random pattern generator in built-in self-test. Second is it is used for encryption, scrambling and error detection. And the third one is it is used for pattern generation for simulation and testing. You can take another example for pseudo-random sequence. Let us take an example. Here is QRST and XOR gate is two inputs of this XOR gate are connected with S and T. And here you are getting the output for this XOR gate, and this is input to this Q. Let it be this is a flip-flop, Q flip-flop, so that is connected to the initial Q flip-flop. It means here is a XOR gate, in between it is connected X3 and X4, and we are getting the output in the form of X0. So let us take an example, Fx, X4 plus X ki power 4 plus X ki power 3 plus 1. So cycle length is 15. So first we are taking the example of 1, 1, 1, 1. So we have to find out that when we are applying this 1, 1, 1 in this circuit, so it will repeat after 15 cycles. Except when QRST is equal to 0, 0, 0, it remains logged, no change in the state if we are taking an input of 4 times 0. But other than this, we are getting the output and it will give you repeatable output after some interval of time. Now, so here BILBO, so this is random logic base. So built-in logic block observer, this is a set of flip-flops with additional test circuitry. It is operated in multiple modes as a scan chain, as a linear feedback shift register pattern generator, as a linear feedback shift register based response comparator, or as a normal D flip-flop during the regular operation. So what do you mean by, here's some definitions you should know. What do you mean by built-in logic block observer? What do you mean by concurrent testing? What do you mean by circuit under test? What do you mean by exhausting testing? Now, so we will cover this concurrent testing. So it is a testing technique that detects faults while the circuit is performing in normal operation without hailing the system. It means it helps in identify fault in real time. Now, the next is circuit under test. It refers to the specific circuit or module where we have to, the circuit is being tested and we have to find out the faults. If there is fault while comparing the computed output and the actual output, so we have to repeat the whole process. Now, next is exhaustive testing, a built-in self-test method where all the possible input combinations for an input and we are getting the 2 ki power n patterns are applied to the circuit. Now, it also ensures complete fault coverage, but it is impractical for large circuitry for a device. Now, next is irreducible polynomial. So, here it is defined as a Boolean polynomial that cannot be factorized into smaller polynomials over GF2. So, such polynomials are used in linear feedback shift register design to generate maximum length sequence. Now, next is linear feedback shift register, a shift register with feedback implemented by XOR gate based on an polynomial. Already we have discussed with a suitable example in the previous slide that how we can do linear feedback shift register. For example, we are in the previous example we are taking a 3 D flip-flop, 1 XOR gate, and there is a loop. When we are getting the output from the flip-flop third, then that is the input of the flip-flop 1. So, it is also used for generating pseudo-random test patterns. Second is compressing test responses, means signature analysis. Now, here third one is creating maximum length sequence when designed using irreducible polynomials. So, these are the steps where we have to use here linear feedback shift register. Now, we can take a BIST process. First, we have to do a test. So, this is a test controller where we have to perform a test. So, here circuit under test where there is with optional modifications. So, input multiplexer is applied to the circuit under test and we are getting the output response here. When we are applying primary inputs to this input multiplexer, here we are doing the circuit under test, we are getting the output and output, where here we are getting the output here, and by this test controller actual output is also here comparing with the computed output. Now if there is an error, so we can say the circuit is faulty. If there is no error, then circuit is in a good state. So this is all about BIST process. Now next term is signature analyzer. So our response if we are getting a response, we are giving some input and we are encrypted that input, that is, and we are getting output in the form of encrypted form, and we want to get our output in the actual form, then we have to do a decryption. So that is known as we are sending data in sub encrypted, or we have to do a process like decrypting. So that is known as you are getting output in form of signature. So our response compactation technique used during circuit testing. So output responses of the circuit under test are compressed into a short signature using the hardware like a linear feedback shift register. A known good signature from the fault-free circuit is stored for comparison, and that is also during testing the actual circuit signature is generated and compared with the good machine signature. If these two signature matches, the circuit is assumed that is a fault-free, and otherwise a fault is detected in the circuit. Now the purpose for this signature analysis is that to reduce the amount of test data stored and analyzed while still detecting most faults efficiently. Now the second is output response analyzer. Already we have studied in circuit under test. We are getting the output from the circuit under test. We are getting output in here, and we have to analyze the output here by comparing the actual and the computed output. So what are the limitations for this output response analyzer? If both the circuits have the same fault, the output may still match. Such faults remain undetected. However, the probability of the identical faults in both the circuit is very low. So what is the purpose of this output response analyzer? It provides a compact, efficient way to check the test results without storing all the expected outputs. So this is an example of linear feedback shift register. We can take another example that we are taking 5D flip-flops are there, where here 2 XOR gates are there. We are applying here the inputs by these XOR gates, and clock is connected here in all the flip-flops, and we are getting output in the form of X0, X1, X2, X3 and X4. So we can start with this linear feedback shift register with this 0, 0, 0, and when it will repeat, then we have to stop there and we have to find out the period of the cycle, that after this time period your output is repeated. Now you can refer this topic from this Kang book. Thank you.